in the determination of S8. And then I'll talk more specifically about the tension with CME and how some experiments have been quote unquote solving this S8 problem. Then I'll talk about the HSC, which was the experiment I was able to play around during my stay at Cable UPNU, and how we can use the data from very small scales by making a better modeling of baryonic effects. Now I'll show the results and the conclusions and next steps. So I think I don't need to talk much about this, but we have our benchmark model, which is lambda CDM. And usually we want to infer from the large scale structure things like the primordial amplitudes or the energy content of the universe or the expansion rate, things like that. And sometimes we can have some derived parameters like sigma A, which is like a parameterization of the fluctuation amplitude today. Sometimes you have parameters like S8, which I'll explain later. What is it? But it's basically a combination of other fundamental parameters. But usually it's not always like this and not only this. This is very sensible to your experiment, to what their experiment is probing. But in general, like a general picture in large scale structure, the most fundamental way to infer lambda CDM from the large scale structure, usually through what we call 2-point functions, correlation functions. So basically you have a field in the sky and you take its contrast usually. And if you consider that it is often difficult to predict this, the exact field through theory, you actually take its statistics. The most fundamental way is taking the 2-point statistics. And if you consider that your field is approximately a Gaussian variable, then the 2-point correlation function is the object that contains all the information about your field. So this is what we call like a data compression, because not always our field is Gaussian, but it is true that it contains most part of the information about the field. Of course, you can do this data compression in other spaces. For example, you can do the same thing in harmonic space. So you decompose your delta field into spherical harmonics, and then you compute the correlation of these harmonic modes given the power spectrum or the angular power spectrum. And the crucial thing that I want to highlight here is that if you're confident about your theoretical model, that if you infer cosmology through one compression or the other should make no difference. That's the crucial point that I'm going to return later. Now let's try to make this, use this framework in the context of galaxy shear. So this is the most heavy part, but stay with me. So, so galaxy shear is basically the distortion of the image of a galaxy due to the gravitational potential along the line of sight. So basically you have a source and its light travels to us and it's distorted. And what we see is actually this image. So if you think that your unlensed position in the sky is theta s, and it's transformed along the line of sight to theta, then this transformation you can think as a means of a Jacobian, basically. So this Jacobian, if you compute this, it's basically the identity plus a tensor that we call the distortion tensor. And this distortion tensor is basically the partial derivatives of what we call the lensing potential, which is basically an integration of the matter field along the line of sight.
So, but this potential is projected in the sky, depends only on the angles. Oh,
What?
the potential in principle is 3 dimensional. It depends on the 3 dimensions. But you are projecting into the sky, or you keep it 3 dimensional.
No, you're projecting in 2 dimensions.
Okay. So it depends on the 2 angles.
I mean, yeah, it depends. I mean, it's implicit here that the image that you're seeing is at a certain redshift, right? So this effect here is an integration of the matter from that redshift up until us.
Okay, so is the potential resulting from this integration?
Yes,
Fine.
basically, yeah. You can go further and decompose this distortion tensor into 3, let's say, main components. So this distortion we can think as a sum of 3 components that we call the convergence, which is responsible to the augmentation of the image. And then you have the spin 2 field that we call shear, which causes this distortion, the image. So so this is the distortion tensor, and when you look at it, it contains the information, as I said, about the matter content along the line of sight. Now it's easier to compress this information in Fourier space, because if you go to Fourier space and make the composition in analogy to polarization, you see that this tensor, it's actually a pure E-mode field. So this is just a consequence of the gravity producing only E-mode distortions or curve-free distortions. Now, this E-mode, if you do the calculations, is basically just the convergence in harmonic space or Fourier space, if you will. So this convergence, as I said, is basically just an integral along the line of sight of that. So from the position of that image up to down of the matter content in the universe, with this object Q that we call the lensing efficiency, which is basically just a kernel and accounts for all the matter that is present along the line of sight. So in Fourier space, the data compression of galaxy shear is basically the 2-point correlation function of this convergence. So this is what we call the EE power spectrum, if you will. So it's basically this integration along the line of sight of the lensing kernels for 2 objects at a redshift bin I and J, and the power spectrum of the matter. So this is something very nice about galaxy shear, because it's unbiased. So it tells you it's probing the total matter along the line of sight.
This is an approximation, right?
Yeah, this is an approximation. Yes, it's kind of unbiased.
No, the linear
Oh, yeah, this is the Limber. Yeah, this is the Limber approximation. Actually, the true relation would be an integral with special functions, try to stuff. But this is valid in a flat sky approximation. Now we can try to make this same data compression in real space. Now to do this, it's useful to define the shear components in rotationally invariant components, which we call gamma t, which is the tangential component of shear, and the cross component of shear. And then with this is basically this transformation with respect to gamma 1 and gamma 2. And using the fact that in harmonic space, gamma 1 and gamma 2 are just projections of the E mode, then you make this very clever combination of gamma t and gamma cross, you transform to real space, and then you have this two correlation functions here that I call psi plus and psi minus, which are yes.
Sure, I understand. Are you saying then that there is redundant information in kappa between gamma 1 and gamma 2 in the sense that
No, no, no. No, the thing is that gamma 1 and gamma 2, they are basically objects. It's a spin 2 field, right? So gamma is a spin 2 field. So you decompose it into gamma 1 and gamma 2, right? So in real space, they're not actually there's no degeneracy, let's say. They don't contain redundant information. No.
gamma 1 and gamma 2, but when I look at the last formula, it looks like gamma T and gamma cross, they are built out of gamma 1 and gamma 2. And
Yes.
and then you express them in terms of CEE.
Yes.
CEE itself is relative to kappa, right?
Yes. Yes.
So it seems like you can use one from the other or something like that.
I don't think so. I mean, they are different by this Bessel functions here. So these Bessel functions, they are orthogonal with respect to each other. So I don't think they are there is redundant information.
Maybe, yeah, but kappa, gamma, and gamma 2 have different kind of information, but then you show a formula that
No, but yeah.
suggests to me that
Oh,
somehow they are.
Okay, I think I got. So kappa is related to gamma 1 and gamma 2. There,
That was my question.
yeah, yes. So you can actually obtain kappa from a sum of gamma 1 and gamma 2. Yes. Yes.
Things that it's very hard to measure kappa, right?
Yeah, yeah.
You
That's-
can
that's-
only measure gamma 1 and gamma 2.
Yes.
It's unmeasurable because you don't know the intrinsic size of the gas.
Yes. Sorry. So yeah, so this is a clever way of computing let's say the data compression in real space of gamma 1 and gamma 2 is through this psi plus and psi minus correlations. Yes. So this is what we call the shear 2-point correlation functions. And then that's it. That's the two things that I want you to remember. So if you want to make a measurement in harmonic space or Fourier space, what your theoretical object of interest is the CL, so the power spectrum. And if you want to make your measurements in real space, then the theory is just a convolution of this power spectrum with these Bessel functions. Now, it's useful to try to understand what are the cosmological parameters that this shear is sensible to. So if you look at the lensing kernel, so the lensing kernel is sensitive to basically H0, omega matter. And if you look into the power spectrum part, it's at linear order dependent to an amplitude, which we can parameterize by the sigma 8. So we can think that at leading order, the CL is proportional to sigma 8 squared times omega matter elevated to some exponent. So the response at first order to the variation of CL to respect some parameters is given by this thing right here. So if you say that this thing is constant, then you have a degeneracy relation between sigma 8 and omega matter that is given by this combination right here. And we just make this convention where we call this quantity S8, which is basically the degeneracy that you have in the measurements of CL. So this is the thing that galaxy shear experiments are most sensible to. So we can go now, make experiments, try to constrain this S8 value. And one funny thing that happens when you try to do this is that at least in the first probes around 2019, 2020, ES kits and HSC were giving S8 values systematically lower than the Planck values, which is a probe at the CMB. Now, there's another very interesting thing going on these first experiments, that if you make the data compression in one space and infer S8, and you do the same thing but on the other space, some experiments like HSC and kits, for example, were given to, let's say, incompatible values, which is kind of strange because you're compressing the same field. You should expect that if you compress in real space or Fourier space, should make no difference. And you're seeing an incompatibility of 1 sigma. So let's try to understand this, and then we move on to the SA tension with Planck. So these incompatibilities of S8 inferred through real space or harmonic space can be understood as a means of scale cut problems. So here's the general picture. So when you're doing analysis in galaxy shear, usually you want to cut your data at some point in which you don't believe, you don't trust anymore your model. So something around the multiple 2000s. Above this multiple, some nonlinearities starts going on, such as intrinsic alignment, PSF, which is just the distortion of your camera, and baryonic feedback, which I'll talk more about later. So you cut, for example, I'm doing analysis in Fourier space. I will cut at multiple 2000, and then the logical thing would be to if I make the cut at 2000 in Fourier space, then in real space I would make the cut at y divided by L. But the thing is that making this cut is not a very good choice. And to show this, first, the reason why it's not a good choice is because of this relation right here. You see that the psi of a certain theta is just a convolution of the CLs, but this is a convolution up to L infinity. One could argue that if this L theta term goes higher than pi, then this circle this Bessel function goes to 0, but that's not really the case. So if you see this plot right here, this is basically the compatibility of integrating this function right here up to this L max versus integrating up to infinity. So take a look at this yellow curve. So this is the psi of theta for arc minutes, which is by this relation here, L 4500. So this dashed line here is L 4500. You see, if you integrate up to this L only, you have a 20% error in your estimate of psi. Actually, to have like something like a 5% error, you must integrate this expression right here up to 10,000. And if you want a 1% error, you must integrate to 40,000. So it's 10 times more multiples than the actual scale given by this relation right here. So the main takeaway of this is that a psi of this angle resolution is much more sensible to small scales than this CL Lmax, because it contains information about all these higher multiples than this Lmax right here. But that's the main takeaway. So in practice, if you make like an analysis up to L2000, you don't cut at minimum theta of pi divided by Lmax. You make your analysis cutting much higher in general. So how do we solve this in real life? So in real life, what you can do is basically defining this relationship between a maximum multiple and a minimum multiple, not by this relation right here, but by a physical cutoff Kmax. And it's basically saying that if you integrate all your signals, so all your CL up to a Kmax, making this change of variables right here, it must contain 95% of your total signal. So in other words, if you do this integration of your total signal, either being CL or psi, only 5% of small scale effects must be present. And that's the way people usually do scale cuts into different analysis today to make this analysis consistent with each other. So for example, here is the relation between Kmax and Lmax, and this is the relation between Kmax and theta minimum. And it's nice to see that psi plus and psi minus actually have different values of theta minimum. Usually, theta plus, you want to make much more aggressive scale cuts than theta minus, which is kind of interesting.
So in this plot, can you point me where for a given what is the K?
So here you're making a cut at, for example, at 3H divided by megaparsec, right? So it's this dashed line right here. You see?
Okay.
So for each redshift bin, you have a different Lmax that you must cut. And then then you do the same thing for the real space analysis. So for this Kmax, and for each bin and for each type of correlation, so psi plus and psi minus, you have a different cut
Okay.
in theta. Yes.
But then I would like to see if a definite cut in theta will correspond to some L.
So that's the thing, that we don't have this relation no more. We have.
No, I know. That's why, I mean, the naive relationship, theta equal to pi over L, would it correspond there?
So the thing is that we don't have this relation anymore, right? We make a scale cut at Kmax, right? So we make a scale at Kmax, and then we obtain the Lmax and the theta minimum. So that's basically the relation. You fix a Kmax, right? And then you have your cuts in the multiple for each bin, and you have your cuts in theta for each bin.
But you could.
I mean, yeah,
Forget about this. Let me just say, what is the theta min for? Max there, right?
Yeah, I guess you could make a
Yeah, to make it easier.
yeah, yes, maybe
Maybe
you
it
could
would be
make
something to the left of those dotted lines. Typically.
yeah.
Okay, that was my phrasing my question.
So that's the idea.
You divided the different redshift bins. Is the redshift increasing or decreasing for 1, 2, 3?
Oh, it's increasing.
Increasing.
Yes.
Oh, so for bigger redshifts, you need more.
Oh, no. Oh, I'm sorry. I think it's decreasing, actually. I think it's decreasing because the closer you look, the more nonlinearities start to appear, right? So usually I think you want to cut further, like at higher values of theta, for example. Yeah, I think that's it. The fourth bin is the closest one. Yeah, I think the fourth bin is the closest.
Yeah, the plot on the left hand is that, so you're pushing the L's to be higher as for higher redshift.
Yes,
Plot on the right,
it's the contrary, right? Because here you're going to from very low scales to high scales, right?
okay, right.
It's the contrary, so that's why it's split. So there are another ways of making this analysis in one space and the other consistent, but this is the general way that people have been doing things lately. So for example, if you take HSC, which had this problem, so in 2023, they did the analysis in both spaces using these consistent scale cuts, and then the S8 value got pretty compatible, like 0.1 sigma with respect to each other. So that's nice. But at that time, there was still the problem of the S8 tension with Planck. And every single experiment on galaxy shear had this problem. And this was around 2020, 2023. But recently, there were some very interesting developments in this whole S8 tension drama. So for example, earlier this year, Kids Legacy was released, and they made something about the photo zoom calibration, and then they reported an S8 value which is basically on top of Planck, so it's pretty consistent with Planck. And also last year, the DS collaboration, they reanalyzed the DS year 3 shear data with blue galaxies only, which are thought to be less sensitive to an effect called intrinsic alignment, which I'll explain in the next slide. And then with this blue galaxies only, their values for S8, independent of the model that you use for intrinsic alignment, or even if you don't use modeling to intrinsic alignment at all, they're very, very consistent to the S8 from Planck. So let's try to understand what's going on with both of these probes. So first of all, let's try to understand what is intrinsic alignment. So it's a very simple idea. It's basically the fact that galaxies are not round. They have intrinsic ellipticities, and in general, they are not actually randomly oriented, right? They usually respond to the tidal field. So what you're actually measuring when you're measuring the galaxy shear is actually the combination of 3 relations. So the shear caused by gravity itself, the cross correlation between the intrinsic alignment and the gravity shear, and the intrinsic correlation. So there are two main models to model this intrinsic shear. And the first one, it's called NLA, which we call nonlinear alignment, which is basically modeling this intrinsic shear to be proportional to the tidal field. So you make this modeling, then your shear correlation will have this II and GI new components, which are basically linearly dependent with the power spectrum. And basically what you have is are 2 parameters. So A1, which is basically the amplitude of this intrinsic shape, and a slope, eta1. And then you can go further and make a model which we call TATT, which is, I think, the the most sophisticated and a model that people are using the most right now because it's more flexible. Basically, it basically it's adds the tidal alignment, which is basically NLA, but it adds a second term expansion in the intrinsic shear, which we call tidal torquing. And people also usually add a bias to the intrinsic to the tidal alignment, and then you have a theory that's dependent on yes.
Because I thought you were distinguishing something intrinsic to the galaxy that has to do with the way it was formed. With something that has to do with the environment in which the galaxy is, and the environment is the tidal field of all the other galaxies nearby. And now I don't understand because the NLA seems to be saying that the intrinsic is given by the environment, as if the gravitational was proportional to the intrinsic. I don't know.
I'm sorry, I don't think I understood your question.
I'm going to try to reformulate. So you said there are no types of alignment, sources of alignment, an intrinsic one and a gravitationally induced.
Yes.
So the gravitationally induced, I understand, it has to do with the fact that the galaxy is in some gravitational field.
Yes.
And the intrinsic, I would imagine, is just has to do with the way the galaxy was formed somehow historically.
Yes.
But
And
say NLA is
and-
the intrinsic alignment is determined by the tidal field. So it seems like now you are relating the two. It's not independent anymore. Or I misunderstood this equation.
I'm sorry, the intrinsic alignment, this is basically a model to the intrinsic shear, not the total shear. So it's
And
basically an expansion of the tidal field.
so
and-
why is it called intrinsic if in fact it's determined by the tidal environment? Is it the gravitational one?
I mean, it's not exactly like the gravitational because it's dependent on basically the type of I don't know if I know I don't know if I know how to answer this.
Maybe I can just go back to. I didn't understand well.
It's just that the distortion caused by the gravity is exact. It's caused by the matter field. And this is something that it's something like that has to do with the intrinsic shape of the galaxy, but we don't actually know what is this intrinsic electricity. So we add these parameters A1, beta 1. I don't know if this answered your question, but we can talk about it.
Yeah, I think I'll ask you.
Okay. So these are the two main models for intrinsic alignment. And the thing that basically DS people did earlier last year was to get rid of late galaxies, so spiral galaxies, which are thought to be sensitive to this second part of the TATT modeling. And basically they reanalyze the SER3 data with only blue galaxies. And even if they use TATT, the value is a little bit higher than their, like, let's say, official result. So it's more compatible with the S8 from Planck. And if they only use NLA, which should be more than enough to model these blue galaxies, then your value for S8 is really on top of Planck's value. Now, for the case of Kate's legacy, the thing that they changed in their analysis were mainly two. Basically, what they did, the first thing that they did was to recalibrate this NI distribution of galaxies. So this has to do with something about instrument. And the second thing that they have changed is this delta ZI parameter right here, which is basically a parameter that we let free in the theory to, let's say, marginalize over our ignorance about the true underlying distribution of galaxies. So the thing that they changed actually was to make a new redshift calibration, and they put tighter priors on this parameter here. And they also use only NLA, so they got rid of 3 parameters. And then their result was pretty close to the value of Planck. And in 2 different data compressions, so Cosibis and band powers. So, okay, so kids and DES solved the, let's say, solved, quote unquote, the problem of SA tension. But HSC, which is another very interesting and important probe of shear, didn't. So what's happening with HSC? And the answer is I don't know. I mean, people from HSC did a lot of tests to see if SA changed from their official result, and they didn't. But there's a disclaimer here because they did not change their minimum scale cut. So they only took data from like L2000 downwards. And maybe this is just like some statistical fluke. There are too many parameters and not that much data that they're working with.
So just to be sure, not poor data in the sense of the imaging of HSC is better
No,
than
no,
all the
the
others.
HSC
Just
has
not enough
yeah,
data.
yeah. The HSC
Too
has
little data, not too poor.
too little. Maybe the choice of words was poor. But yeah, the HSC has one of the best cameras, some of the Edison. But one thing is for sure, they don't have few data. They just chose to cut most part of their data. So this is a plot of psi plus and psi minus. So, and all the autocorrelation and cross correlations. And the gray shaded region are all the things that were cut in their official analysis. And the reason they cut all this data, 2/3 of the data, was I think was basically that they were not confident about modeling this very nonlinear physics, mainly baryonic feedback. And maybe they were afraid of maybe upsetting their beautiful crafted relationship between the scale cut in the real and harmonic space, but I don't know. So the idea of the project I've been doing with Elisa is basically model better modeling of the baryonic effects and try to use all of this unused data because this has information. It's gotta have some information about cosmology, and it's gotta inform us something about the SA tension maybe. And in the eventual incompatibility of real and Fourier space, it will basically tell us something maybe is wrong with our modeling. So this is actually making the analysis in both real and harmonic space can be something complementary. So this is the thing that we're going to do. Now, I want to explain first what is baryonic feedback. And I have this very nice video from Francisco Vilescusa from CAMOS. So basically, baryonic effects are these subgalactic processes, mainly AGNs, supernova. And the thing is that they these processes, they modify the distribution of matter at this very low scales, typically at the scales of a galaxy. And then you have enhancement or a suppression in your power spectrum at this very low scales. So that's the basic idea. The problem is that we do not know exactly, like Fernanda said, we don't know exactly what is driving these processes in the galaxies. So each hydrodynamical simulation has a different way of modeling the baryonic feedback. So each one will have a different strength to the suppression, a different scale dependency. And this is something that we are pretty ignorant about. So what people have been using in the official analysis. I think the most famous is the HM code, which is an analytical modeling. It was used by KIDS, HSC, and DES. And the main idea is basically that HM code will modify the halo concentration. And with this a baryon parameter here, and it will change the scale dependency of the halo density profile with this halo bloating parameter that can be parameterized basically by a baryon too. So this is just a one parameter model. I mean, the official HM code has a lot of parameters, but usually people in HSC and kids only use this only one parameter, which is this a baryon, which is responsible for the strength of the suppression. And this is a plot from people of HM code, which shows that at least for the hydrodynamical simulations they're validated against, HM code is very capable of explaining the suppression of the power spectrum. So the problem is that HM code is validated only on 2 hydrodynamical simulations. So it can be that the true baryonic effect feedback in the universe is not explained by these hydrodynamical simulations. So this is one concern. Now, what happens if you reanalyze HSC real data without excluding anything, without making scale cuts? And this is something that Yo Terasawa, which was a colleague of mine at Kavli, already answered. And the thing is that if you use an HM code and don't make any scale cut, first, there's no gain in constraining power for all of the parameters of HSC, and the tension is still present. So, okay, that's interesting. But one thing is that they didn't do this analysis in harmonic space. So this is something that I'm going to do to verify that this value of S8 is the same in harmonic space, to see if we can really trust HM code on such small scales. So to make a better model of baryonic feedback, we're going to use Baku, which is basically an emulator of the power spectrum, which also incorporates baryonic feedback, the baryonic suppression in the power spectrum. The Baku was computed with a method called baryonification, in which they basically take an n-body simulation made with dark matter only particles, and then given a prescription given by these parameters right here, they shift the positions of the galaxies to simulate a baryonic process, and this ends up suppressing the power spectrum when they compute this power spectrum. So they make lots and lots of these simulations, let's say, with this baryonification method, and they compute the power spectrum, and then they emulate this for many values of these parameters here. And the nice thing that made us want to use this is because it's validated across a wide range of hydrodynamical simulations, not only two. It's validated for Bahamas, sea owls, illustrious, eagle. So it looks very flexible. I think that's the word. So this is what we're going to use. And for now, what we have done is to reanalyze the HSC year 3 data and in both spaces, so using CLs and using the size. And the two main scenarios is basically we're going to use HM code. The first one, use HM code to model the baryonic feedback, just like the official analysis. And then we're going to use Baco to see if something changes. So the main plan here is to basically, for each, we're going to make a lot of scale cuts. So we're going to include more and more data points to see what changes in the cosmological parameters and the intrinsic alignment and baryonic feedback parameters. And that's it. And just for a disclaimer, so the first scale cuts here, like 2000, is around the official scale cut. So we're going to add more and more data up to 14,000 multiple. And the first scale cut in theta, it's 8.4 arc minutes, which is around the official scale cut, at least for psi plus, because for psi minus, it's actually 40 because of that story of making scale cuts consistent. They actually made different scale cuts for psi plus and psi minus. But here we're going to do a single scale cut for the two spaces. And I think it's mostly to highlight some eventual incompatibility between the results in real space and harmonic space. So that's it. So these are the preliminary results. So how to read these plots? Basically, the blue lines are the best fits for in the harmonic space analysis. The yellow are the best fits for the real space analysis. And as we go from left to right, we're including more and more data points. So we're going to lower and lower scales. This is the scenario in which we keep everything just as the official analysis of HSC using HM code. So it's just one parameter for the baryonic feedback. And one thing which is really surprising is that if you make the, let's say, official scale cuts, the values for S8 are very inconsistent. Especially the real space, the value for S8 is very low. But the value for S8 in Fourier spaces, it's much higher and actually more closer to the Planck's value. And as you go adding more and more data points, these things seem to go up. So the S8 tend to increase. So the final values, if you include all data points in Fourier space, is actually S8 around 0.8, which is actually very close to the value of Planck. And in real space, the result was pretty close to Yo's result. So this means that we're probably making the analysis right. So that's something good. But the strange thing is that there's a huge inconsistency between the two results.
So João, I mean, naively, you would expect actually that, you know, with less information with the lower Lmax, that that the scatter could be larger, but that they should already be closer, right? So,
Yeah.
I mean,
It-
you're adding more information, you're making things, including more information, making it more predictive in a sense, but it started off even with little information being in conjoint intention there, right? So, this to me doesn't look like it's only a matter of method and modeling and so on, but there's something more basic in the data even, right? Or maybe, I don't know, and why would, even for a very low cut, the SA come out so different? I mean, let's say,
Yeah.
make L max equal to like, I don't know, 500. At some point, they should coincide, right?
Yeah, it's just to, I mean, as I was doing this analysis, I started doubting the data from HSC because things looks very like inconsistent. Like if I did the same scale cuts from the official analysis, probably this thing would match because I'm not making the official scale cuts. The Psi plus, I'm actually taking more data, right? Because I'm making a single scale cut for both Psi minus and Psi plus. But this is, for me, is an indicative that the HSC results are very fine-tuned. So, like they fine-tuned the scale cuts just for the essay in both spaces to give the consistent answer. For me, it's something like that.
You will never know.
Yeah. I think I'll never know. Yeah. So yeah, these are the results for the HM code modeling. Now, if you use Baco, something interesting happens. Even for the case of real space, the value for S8 goes up. So this is something nice, and it starts to get a little bit more consistent between each other. One nice thing is that different from the HM code case, all the cosmological parameters seem pretty consistent along all scale cuts, except maybe for sigma 8 and S8. But the nice thing here is that first, if you include all data, they seem, even if you don't include all data, they are a little bit more compatible with each other. The second nice thing is that sigma, I didn't comment on the last plot, but sigma 8 here is much more close to the Planck's value. So in the HM code case, sigma 8 is very high. So it's almost reaching 1 for the Fourier space. And when you go to the Baco case, this value for sigma 8 lowers. So it gets into a much better agreement with Planck. And also S8 for the map. Of course, you have Baco has 7 parameters to model baryonic feedback. So it's a lot of parameters, and we cannot say much about all of them. They are pretty much prior dominated the last 6 parameters, and only the first parameter is well constrained. But it's a little bit concerning because it seems like it wants to go out of the validated region of Baco. It tends to a very high value of this MC, which is basically a parameter that tells you about the suppression of given by the baryonic effect. So the higher the MC, the higher the suppression. So it's telling us that HSC has a very, very high baryonic suppression effect. So this is something that maybe we could tell people from Baco, because I don't think that the same thing happens for other probes. I think I read a paper from Baco, and they said that this high suppression doesn't help. That doesn't happen to DES and KIDS, for example. So we did the same thing, but just adding the Planck priors just to anchor the cosmological parameters to see if anything changes in the intrinsic alignment and baryonic feedback parameters, but nothing really changed. So I don't think I have anything interesting to say right here, but nevertheless, I'm showing the plots. The things, at least the parameters for baryonic feedback stay the same. And that's it. I'm going to conclude right now. So the conclusion is that first, there's no significant increase in constraining power by adding all of the data. But this is something kind of expected because we are adding 7 additional parameters with Baco. So one thing compensates for the other. But we observed a tendency of increasing the value of S8. The other thing that we concluded is that using a more sophisticated or more flexible model for baryonic feedback seems more consistent. And not only for the parameters, but if you include all the scales, first, S8 seems lower and inconsistency with Planck, and also S8. S8 is higher than using N-shaped code and alleviates S8 tension in both spaces. I think this is one of the important things to say. It's consistent. It's consistent in both data compressions. Still, it's hard to say what's driving the S8 tension in HSC data, and also in other experiments, because it seems like different probes have different ways of solving it. So this is something to investigate, and we actually want to make the same changes that people from KITS and DS made to see if this also alleviates the S8 tension. So we want to play with intrinsic alignment modeling. We may want to maybe play with the priors on the calibration of photosys and see if this also alleviates the tension. So these are some of the things that we want to do now in the future. And that's it. Thank you.
I have a few comments. First, I never lost my sleep because of S8 tension.
Yeah. Nowadays, I don't think the S8 tension is that like taken so seriously.
Yeah, and then the other thing is, you mentioned a paper of Cyril Du.
Yes.
And you mentioned in 2021 paper, if I'm not mistaken.
Yeah.
That's why.
Yeah, I think it's 2020 or 2021.
Because there's, I don't know, because it has 2 papers, but I want to call your attention to the paper 2022, where he does, well, we do actually, because the whole collaboration, part of it. The shear analysis in harmonic space. So DS, of course, the analysis is in the fiducial analysis is in real space, and the harmonic space is not. So it's an alternative analysis. No? But Cyril led this very interesting paper in 2022. And in this paper, we reached the conclusion that actually the tension decreases if you do things in harmonic space. So there is a difference, and the tension reduces to 1.5 sigma. Now, the other thing I want to mention is that there's a paper of 2024 doing the, again, DS year 3 analysis in harmonic space of galaxy clustering, galaxy lensing. That's led by a student at USP, Lucas Paga.
Oh,
So he led this, and this is published already. And in that analysis, so again, it's not shear, but it's the other 2 things. And it depends on the catalog that he used for the clustering. In the S, there are 2. One's called Red Magic, other is called Maglean, and the results depends a little bit on 2. It's not a little bit, it's actually 1 sigma difference, let's say. And the year 6 analysis are coming up in 1 month, so we know what is the results for say shear and also from 3 times 2. And we actually worked on 3 times 2 for DS year 6 in harmonic space, and also that's led by Lucas, and I think my student Guilherme is also starting to do this. And finally, the other thing I want to say is that there is another way of taking into account the baryonic effects, and that you can do modifying the covariance matrix. So the idea is that you have this 13, let's say 13, 14 simulations, and then you assume those are a statistical distribution of the possible errors, and include that in the covariance matrix. And this is something that a student, master student did a couple of years back, Gabriela did. So this is called the theoretical error. So include this error in the covariance matrix. And so in this way, you don't need a sharp scale cut, but you do in such a way that when you go to large values of L, what happens is that the covariance matrix or the errors become so large that they don't, they lose their significance, let's say. So, but there's no sharp cutoff. So this is a paper that you may be interested in taking a look. So it's Gabriela Moreira et al. I think 2022 or something like that.
I think it's a similar idea, right? Here we are adding parameters and marginalizing over them to
Yeah,
account for our ignorance.
yeah,
You are putting for our ignorance in the covariance matrix.
right. Using
From the
the
results.
different hydro simulations
Let's see.
as a statistical thing.
Nice.
So you can take a look.
Yeah.
And then
That's very
you may be interested in it. But people are not using this. I wish they were. Okay.
Any other question? Yep.
So thanks for the talk. I didn't get why once you add the baryonic effects to lab or a chemical, why is the consistent scale cut not important?
It is. Oh, it is, but I think the idea is that we want to highlight I mean that deliberately chose not to use this consistent scale cut just to say that okay, if it's wrong, if the results are inconsistent between real space analysis and harmonic space, it can be two things. It can be an inconsistency in the scale cut, or it can be an inconsistency in the theoretical model. But if it's consistent, then much probably this thing is okay. So the modeling is okay. So I think it was more like a conservative approach.
Yeah, by the way, for DS year 1, we also made this analysis, seeing whether or not the harmonic space in shear is compatible real space. So I think this was led by either Hugo Camacho or Felipe. But that's year 1. But let's wait for that year 6.
No more questions. Okay, so let's start.
Wait.
No.
Now we have to decide the dates for the following.
Oh, always.
Okay. Good.
Thank you.
Sorry, because you see, apparently today it was reserved. Luckily, they didn't use this room, so we could use it. But it's better if we reserve well in advance. So it's almost September, so we could have next meeting. What is either
26th of September
yes,
or 3rd of October.
yes. Do you have any preference? Somebody is more likely to be present in one or the other? Okay,
Yeah, we both days.
both day, okay.
Not for long.
Shall we say October the 3rd? Okay. And then we jump to 31st, and 31st is Halloween, but it's not holiday in Brazil, so. So in November, when do we want to do it?
That's on Halloween and everyone brings a fantasy.
Yeah. Halloween is okay. Ah, no, wait, I won't be here in sorry, I won't be here. This specific date, I won't be here, but I mean, I'm just one, so.
Sorry, I think for me, the 3rd of October is bad, actually. I prefer the 26th.
So I have no
November. Is that
preference.
okay? Sorry,
Anybody has any preference? So 26?
for me, it's better, so.